We have learnt that, when a current passes through a conductor, it exerts a force on a magnet, which is placed in its vicinity. Is it possible, if this process is reversed? A French scientist named André-Marie Ampère suggested that a magnet must also exert an equal and opposite force on a current-carrying conductor placed near it. Let us observe an activity to demonstrate the force caused by a magnetic field acting on a current passing through a conductor. Take a small aluminum rod and let's call it AB. Suspend this rod horizontally from a stand, using two wires, which is connected to the stand, as shown here. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. The north pole has to be placed vertically below the aluminum rod, and the south pole has to be placed vertically above the aluminum rod. Connect the aluminum rod in series with a battery and a switch. Now turn on the switch. What do you observe? The rod is displaced towards the left. This suggests that a force is exerted on the current-carrying aluminium rod when it is placed in a magnetic field. What happens when we reverse the current? The rod moves towards the right. This means that the direction of force is reversed when the direction of the current through the conductor is reversed. And, if the poles are interchanged, the force acting on the conductor gets reversed. This shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shown that the magnitude of the force is the highest when the direction of current is at right angles to the direction of the magnetic field. In such situations, we can use a simple rule, known as the Fleming's left-hand rule, to find the direction of the force on the conductor. According to this rule, stretch your thumb, your forefinger, and your middle finger of your left hand in such a way that they are perpendicular to each other. Your forefinger points to the direction of the magnetic field. Your middle finger points to the direction of the current. Your thumb shows the direction of force acting on the conductor. Devices that use current-carrying conductors and magnetic fields includes electric motors, electric generators, etc. Have you ever wondered how your fan works? The answer to this question is the electric motor. Almost every mechanical movement in electrical devices that we see around us works on an electric motor. An electric motor is a device that converts electrical energy into mechanical energy. The working is based on the principle that when a current-carrying conductor is placed in a magnetic field, it experiences a mechanical force. It contains a horseshoe-type field magnet, an armature coil ABCD, which is rectangular in shape. The coil is placed between the two poles of a magnetic field, in such a way that the arm AB and CD are perpendicular to the direction of the magnetic field. Note that the axis of rotation of the coil is perpendicular to the direction of the magnetic field. The ends of the coil are connected to the two halves, S1 and S2 of a split ring. This is called split ring commutator. The split ring commutator is free to rotate along with the coil. Its function is to reverse the current direction after every half rotation. The inner sides of these halves are insulated and attached to an axle. A pair of brushes, B1 and B2, touch the split rings, S1 and S2 respectively. The current in the coil is supplied through these two brushes. A battery and two connecting wires are connected to the brushes. When the coil rotates, the split rings rotate, but the brushes do not move. The current in the coil ABCD enters from the source battery, through conducting brush B1, and flows back to the battery, through brush B2. Notice that, the current in arm AB of the coil flows from A to B. In arm CD, the current flows from C to D, which is opposite to the direction of current through arm AB. On applying Fleming's left-hand rule, we find that the force acting on arm AB pushes it downwards, while the force acting on arm CD pushes it upwards. These two forces turns the coil anticlockwise. What happens in this position after half a rotation? The split ring S1 comes in contact with brush B2, and split ring S2 comes in contact with brush B1. Therefore, the current in the coil gets reversed, and flows along the path DCBA. The reversal of current also reverses the direction of force acting on the two arms, AB and CD. Applying Fleming's left-hand rule again, we get the direction of force. Thus the arm AB of the coil, that was earlier pushed down, is now pushed up, and the arm CD previously pushed up, is now pushed down. The reversing of the current is repeated at each half rotation, giving rise to a continuous rotation of the coil.